The last topic of conversation for equilibrium is conceptually predicting how a reaction is going to change based on what we call a stressor. And this is called Le Chatelier's principle because Henri-Louis Le Chatelier is the one who came up with it back when France was cool. The idea behind his principle is the idea that, like, we understand equilibrium is when a forward reaction and a backwards reaction are happening at the same rate. But, all the questions that we've worked on have had very particular circumstances. Like, it has to be this temperature. And that's because equilibrium depends on the environment that the reaction is happening in. It depends on the pressure that you're at. It depends on how much of the reactants and products you started with or have now. It depends on the temperature, blah, blah, blah. So if you change the system that the reaction is, that is called stressing the system. So if we look at, the seesaw here, essentially what you're saying is you could cause a stressor that would increase where the reactants are at. It could decrease the reactants. It could increase the products or decrease the products. And since systems that are reversible reactions are always trying to get back to equilibrium, once you have stressed the system, the reaction has to move in the opposite direction of the stress. The first type of stress that reactions can have is a change in concentration. So let's say you've got this spicy little reaction going on and you just decide, you know what, like it's at equilibrium right now and I'm just going to add a crap ton of N2O4 to this system. So you've got a chamber, you've got two gases floating around in it, they're at equilibrium, and all of a sudden you pump in a bunch of N2O4. So if we go back to our seesaw, okay, what that means is we are raising the level of reactants. So we are going to set the seesaw up too high, which means that Q and K are no longer equal. And the only way to get reactants to come back down is to shift to the right. So the reaction will proceed forward for a while until the reactants and products are balanced out again. Oops, I accidentally hit pause. So I have no idea what just happened. Anyway, if we switch it up and now our system's at equilibrium again and we decide we're going to add a crap ton of NO2, okay, then the system is going to shift the opposite way. Okay, so now the problem is we have too much product. We've raised the bar on the products, which means it has to shift to the left away from the stress. Okay, this does work in the opposite direction as well. So let's say instead of adding substance, we remove. So if we have a system at equilibrium, we've got N2O4, we've got NO2, and they're at equilibrium, whatever's going on, and we decide we're going to start removing this as it's formed. Okay, now the stress is the opposite problem. The stress now is that the reactants are too low. Okay, so the only way to get reactants to be replaced if they've been removed is to switch in the direction of the stress, because now the issue is reactants are too low, so the products have to turn back into reactants to balance it back out, and vice versa. Okay, if we decide we're going to remove something from this side, okay, that means the stress is a lack of product, so that means we need to shift to the right in order to replace the product that was removed. So looking at a different reaction, okay, everything's a gas, so that means everything applies to equilibrium. If the system is at equilibrium right now and all of a sudden a bunch of bromine is pumped into the tank, okay, that means that Q and K are not equal anymore. Okay, our concentrations of products are too high because we've added bromine, so that means the reaction needs to shift to the left in order to take product away and put reactant on the other side. And vice versa. So if we decide we're going to add more of the reactant, then that means now we have too much reactant, which means the reaction needs to shift to the right in order to balance back out. If we decide that we are going to remove nitrogen monoxide, so now our issue is we do not have enough NO. The only way to replace NO is to have the BRNO break down and decompose to replace what we've lost. So in a removal situation, the stress is the opposite problem. If we don't have enough NO, the reaction shifts to the right to replace what was lost. This reaction is a little bit different because what we have to remember is solids do not count towards equilibrium, but gases do. So in this case, if we have an increased amount of carbon dioxide, yes, we have too much product, because for this particular reaction, K is dependent completely and totally only on CO2. So if we have too much CO2, that means the reaction needs to go back to the left, and we're going to have some solid calcium carbonate forming. However, okay, if our issue is that we add calcium oxide has no role in K, because when we're setting up K, the only thing that matters is the CO2. So that means adding CaO does nothing. There would be no movement at all. The second stressor that can be changed in this system is the volume, but really what we're talking about with volume is pressure. Since we're assuming that probably most of these reactions are gases, since almost every single reaction we've looked at is gases. The example here, okay, this shows, or the first one, excuse me. Example A shows a lower pressure system, so the volume is larger. Okay, the large blue circles are nitrogen, the small, like whitish blue circles are hydrogen, and then the ones that have nitrogen and hydrogen both are the ammonia. So you can see that when the pressure is low, there's not very much product. There's a lot of reactants. So, and the reason is because low pressure, okay, is going to be more suitable for lots of molecules. So there are 4 molecules in this balanced equation. There's 4 molecules of reactants. We have 1 nitrogen and we have 3 hydrogens, but there's only 2 molecules if everything turns into a product. So since the volume is large and therefore the pressure would be lower, those molecules are going to be happier filling up the chamber. So we're going to have lots of nitrogen and lots of hydrogen, because that means that we'll have more moles inside the chamber. If we start to lower the lid of the piston, that's going to decrease the volume, which means the pressure is going to start increasing. So that will put stress on the side of the equation that has lots of moles of gas. So lower volume means higher pressure, which means this is the side of the equation that has the stress. So if we keep increasing the pressure, the reaction is going to shift in this direction, because we're going to go from 4 moles of gas down to only 2, and therefore compensate for the fact that there's less room for the molecules to move around. And the opposite is true if we go backwards. So if we look at C, okay, let's say we have a very small volume, and that means that we have a high pressure chamber. If we increase the volume, that means the pressure is going to decrease. So we have right now a high pressure system. We've got the lowest number of moles that we can have because 2 is less than 4. But if we start increasing and going backwards, making more room, the reaction is going to start shifting to the left, because it's going to start filling up this new extra space by turning into more moles of gas. So if you were given this equation and your question said, how will this system react to a decrease in volume? Okay, decrease in volume means an increase in pressure. The reactant side has 3 moles of gas, the product side has 2. So if we're increasing the pressure, we want to shift away from lots of moles of gas towards less moles of gas. If the question said that we were going to increase volume, that means that we would decrease pressure. So we'll go from low moles of gas to high. Once again, we do need to remember that if we have solids involved in a reaction or liquids involved, that does not affect K. So if we are increasing the volume in this system, the only side of this equation that has any moles of gas is the right. So increasing volume means pressure is going down. That means it would shift in this direction because the products is the only side of this reaction that has any gases to give. If we decrease volume, that means we don't want to have a lot of gas, so it's going to move to the right. To the left. The final condition that can be a stress to the system is temperature, but this is actually kind of the same thing as concentration, because you can look at temperature like it's a reactant or a product. So for example, when nitrogen and hydrogen make ammonia, it is an exothermic reaction, so we can actually look at ammonia and heat like they're both products. But one other way that this could be written is with the delta H symbol. Okay, if it says that the delta H is negative, that means that the forward reaction releases heat, so therefore heat is a product. So if we are, oops, gotta go back. If we're looking at the system and you're given a question that says, which direction will the equilibrium shift if temperature is increased? Okay, that means that we are applying heat to a system that already produces heat. So essentially what we're saying is we're adding heat to heat, which means now we have too much heat, and I'm saying heat a lot and it's kind of annoying. So too much heat means we need to get away from it. So we're going to go in the endothermic direction. So too much heat means move to the left. Okay, if the opposite is happening, if we're reducing the temperature, that's the same thing as saying that we're removing heat. So that means we need to switch in the exothermic direction to heat the system back up. Okay, same thing is true for an endothermic reaction. It could be written like heat is a reactant, or the reaction could tell you that the delta H is positive. So in this case, if we're told that we're heating up the system, what's going to happen? Okay, that's the same thing as saying we're adding heat, but this time the heat is being added to the left. So too much heat on the left means we need to move to the right. If we're cooling the system down, okay, then that's the same thing as saying that we're removing heat. So the only way to replace heat that's being removed is to move in the exothermic direction, which in this case would be the left. So if we were looking at this reaction and you were told the temperature is being raised in the chamber, okay, this is an exothermic reaction, which I know because of the negative sign, so that means heat is a product. So if we are adding heat because we're increasing the temperature, we need to shift away from too much heat, so that means we would move to the left. So once again, we have a scenario with solids, okay, but heat is not a solid or a liquid, so that means we still have to account for it. If we add heat, okay, that means that we are going to cause more calcium carbonate to decompose because we have too much of a reactant that works for the K value, which means we're going to shift to the right and make more carbon dioxide gas. And the last thing, I'm not really sure why they even bother to mention this in the book. The catalyst thing I kind of get. You should know, like, if you add a catalyst, it doesn't make any difference. So if you have a question that says, which direction will something shift if there's a catalyst? The answer is that there is no shift. Catalysts only make the reactions reach equilibrium quicker. They do not change the value of equilibrium. And if it says you add an inert gas, so you have a system that has a whole bunch of gas in it and you decide you're going to add helium, it makes no difference to equilibrium because helium or argon or any of the other noble gases or whatever, they play no role in that reaction, which means they do not affect the value of K.